So this lesson of the chain rule is mostly going to work with exponential functions that do not have a base of e. That's the majority of what we'll look at. And so I start with the derivative of an exponential function of any base. And so the derivative of b to the power of x is b to the power of x times the ln of b. Keep in mind, until now, we've been just only dealing with an e to the power of x. Although it's not wrong. Notice if you change this b to an e and change this to an e, change this to an e, it's still correct. E to the power of x times the ln of e. The ln of e is 1. Because they cancel each other out, essentially, so it's still correct. Right? That's it, as always, for an exponential function. The base of an exponential function cannot be 1, and it must be greater than 0. So that's it. Let me just kind of prove why this is correct. And I start with this little note here, and that's b is the same as e to the power of ln b. And again, if you just look at e to the power of ln b, e to the power of the natural logarithm, those are inverses of one another, and so you can imagine they cancel each other out. So you can see they are the same. Okay. However, I don't want to cancel them out. To prove that the derivative of b to the power of x is b to the power of x times the ln of b, I want to start by writing b to the power of x as what you see here. So instead of b to the power of x, I have e to the power of ln b to the power of x. Right? Does that be, like everything that's highlighted in green is equivalent? Okay, so the reason I'm going to do this is, although what you see on the right is messier than what I have on the left, it is now, I've written it as an exponential function with the base of e. And we've seen before today how we can differentiate that. And so to differentiate what you see on the right, I need to use the chain rule. Because notice, if you look here, we have, actually, I've got ahead of myself. We don't want to use the chain rule quite yet. I'm first going to use an exponent law before I use that, so I've kind of got ahead of myself. My apologies. First, that's when you use my exponent law. I have a power raised to another power. I have all of this being raised to that power, so I'm going to write this as 1 power. So I'm going to write this as d over dx of e to the ln b times x. Now I'm going to use the chain rule. Because I have on the outside an exponential function with a base of e. On the inside, I have a linear function. Ln b is a constant, but it's a constant times x. That's a linear function. And again, I say ln b is a constant because if you look at what we're differentiating here, b is the base of the exponential function, which is a constant. And so I use the chain rule where first I differentiate the outside function, which is just going to be the exact same thing, e times e to the power of ln b all times x times the derivative of the inside function. And the derivative of the inside function is the derivative of ln b times x, which is just just the ln of b. And again, if that seems kind of strange, keep in mind if it was 2 times x, the derivative of 2 times x is 2. The derivative of 7 times x is 7. And so the derivative of ln b times x is ln b. Ln b, again, is a constant value. And now at this point, I can clean that up a bit. I can now take this e to the power of ln b of x. I can cancel that out in a moment. If I use a logarithm law and realize I have a logarithm all times x, I can write that as a power. So I can rewrite this as e to the power of ln b all to the power of x. Actually, sorry, not all to the power of x, just the b to the power of x times the ln of b. So I can now cancel this out, and we have, in the end, what we're trying to prove. B to the power of x times the ln of b. All right, so in doing so, to prove that this was correct, we use the chain rule. I use a logarithm law when I wrote that coefficient of x, or instead of ln b times x, I wrote it as ln b to the power of x. But not a lot of steps, but as always, when I'm showing these proofs, the idea is not that I want you to memorize it. I just want to, we're using some of these skills that we're trying to look at. But really going forwards, you just now want to remember that the derivative of any exponential function is this. All right, so the derivative of b to the power of x is b to the power of x times the natural logarithm of b. So let's use this a bit in a few examples. Let's differentiate this. Function a is 2 to the power of x to the power of 3. Okay, so I want to find a prime here. All right, so for this, I want to use the chain rule, because I've got to realize I have a cubic function inside an exponential function. So first, let's deal with the outside function, which is the exponential function. And the derivative of an exponential function starts off with just the exact same thing, 2 to the power of x cubed times the ln of the base of the exponential function, in this case 2. That said, I'm not done yet, because now that's the derivative of the outside function. Now I have to differentiate the inside function, which is x cubed. And the derivative of x cubed is just 3x squared. There you go, and I'm done. And I guess I could clean this up a bit, really, but not really. I mean, I could change the order of things, but that's all good. So I'm done. Really easy to miss the chain rule there, though. Really easy to miss a number of things. And maybe I'll highlight again the base of the exponential function is what I found the natural logarithm of. OK, let's look at this expression, or function. So 5 to the power of root x, which I'm going to rewrite as 5 to the power of x to the 1/2, just because anytime I want to deal with derivatives, I find it easier to deal with exponents, because I can use the power rule than radicals. That's it. How am I going to differentiate this? Well, again, I've got to use the chain rule at some point. I have a radical function inside an exponential function. So if I want to find b prime, first let's differentiate the outside function, which is the exponential part. So it's 5 to the power of x to the power of 1/2 times the ln of 5. That's the derivative of the outside part. Now I want to multiply that by the derivative of x to the 1/2. Using the power rule, that's going to be 1/2 times x to the negative 1/2. And well, again, this is fine. There are a few things I can do to clean this up. For example, I have negative exponents. So I'm just going to write this without negative exponents. There's nothing wrong with negative exponents, but if I know what the negative exponent means, I might as well show that I know what it means. And so in the end, I'm going to write this as the ln of 5 times 5 to the, I'll go back to root x for the numerator, and the denominator I have 2 times root x. Again, that 1/2 times x to the negative 1/2 is exactly equivalent to what you see highlighted in yellow in the denominator, dividing by 2 times root x. All right, again, keep in mind, though, we were done here, but we also should understand how to get to there. All right, I think I have just one more example before, one more example like this before a sort of final problem. OK, so here, everything is a variable. But I'm differentiating with respect to x, which is always key. So c of x is a to the power of t over x. I want to find c prime. But again, I have an exponential function with a base of a. So how do I do this? I'll do this in a few steps. So I'll write this as first c prime of x. First, let's differentiate the outside function, which is the exponential part, which starts off as just a to the power of t over x times the ln of a. Okay, but then I got to multiply that by the derivative, and I'll do this in an extra step, by the derivative with respect to x of t over x. This part right here, the derivative of that. That said, if I want to differentiate t over x with respect to x, I could use the quotient rule, or I could write this with a negative exponent. T divided by x is the same as t times x to the negative 1, which I prefer. So I'm going to rewrite this as t times x to the negative 1. They're totally equivalent, t being some constant. So really, I can just use the power rule here. So now to complete my derivative, write this other good stuff down. So the derivative of t times x to the negative 1 is negative t times x to the negative 2. And at this point, while I'm done, nor does it say I have to really simplify this, I'll do the same thing I did before. I'll write this without negative exponents. So in the end, I guess I can put this all together as a to the power of tx times the ln of a in the numerator, and x squared in the denominator. And I need to make, there's a t I need to have. I'll put the t, I'm going to put the t right here, times t. And the whole thing's negative, so I'll put a little negative right there. Because again, there was a negative there, so I'll just put it in front of the fraction. But like I keep saying, I don't really care too much. I do care that you understand how I got to this last step, but I don't really, it's not like you have to do that. But going from this step here to this step here is not calculus. That's previous courses. That's, in this case, that's really Math 10, understanding negative exponents. All right, so the last question actually doesn't involve exponential functions. It's just a tricky question that will involve the chain rule. But I have a function here in blue, and the equation of it is the absolute value of x over root 2 minus x squared. That's it. That's what you see in blue. And this goes on and on and on. I'll draw these little arrowheads here. What I want to know is the slope of the tangent line I've shown you. The tangent line I've shown you goes to the point -1, 1. OK, so to find the slope of the tangent line at this point, that means I need to find the derivative at this point and find the value of the derivative. Remember, the value of the derivative at any point is equivalent to the slope at the instantaneous change at that point, really the slope at that point. So yeah, not surprisingly, I need to differentiate absolute value of x over root 2 minus x squared. So one thing to realize is that absolute value of x can be a bit of a pain, except in this case it's not too bad to deal with, because I'm trying to, in the end, I want to find the derivative when x is -1. And so when x is -1, that absolute value up there is going to have the effect of changing the sign. And so right here, let me make a little note. So at this point, I want if x is less than 0. Therefore, actually, I'll use therefore, I'll say. Therefore, the absolute value of x is equivalent to just -x. And if x was positive, the absolute value of x would be equal to just x. The brackets wouldn't do anything. So when I'm going to differentiate this, I'm not actually going to differentiate the equation I gave you. I'm going to differentiate the exact same equation, but with -x in the numerator instead of x. Sorry, instead of the absolute value of x. So I want to differentiate this. I want to differentiate -x over the square root of 2 minus x squared. Notice the denominator, that x that's being squared, it doesn't really matter if x is positive or negative, I'm squaring it. So it's always just equivalent to x squared. So now I don't really need to deal with that absolute value anymore. I need to differentiate this. Well, and actually, to differentiate this, what I really want to do first is I want to rewrite my denominator with a power. So I'm going to actually, what I'm going to differentiate is this, -x over 2 minus x squared to the 1/2. OK, that's what I'm going to differentiate. So how do I differentiate this? Well, I want to use the quotient rule in this case. And so to use the quotient rule, first I differentiate the numerator. So the derivative of -x is -1 times the denominator left alone. And I can write the denominator in either form. If I'm just going to write it out, I actually like the radical version better. So I'll say times the square root of 2 minus x squared, OK, minus the other way around. So minus the numerator left alone, so minus -x or plus x times the derivative of the denominator. So now here's where this form here is more useful to me. So to find the derivative of the denominator, I want to use the chain rule, because I have 2 minus x squared, which is a quadratic function inside a radical function. Or I can use the power rule. So first, I want to use the power rule to bring over the 1/2, leave the inside alone, subtract 1 from that exponent, and then multiply by the derivative of 2 minus x squared, which is minus 2x. So a lot of stuff going on there. A lot of brackets I've got to be careful about. And so just kind of showing you where all this came from. Right, what you see up here is the first part of the quotient rule. That's it. All of this has to be divided by the denominator squared, which, I mean, it's not wrong to write it like this. Square root of 2 minus x squared all squared. But that simplifies down to just 2 minus x squared, the square root of all that times itself. You can imagine the square root and the power of 2 canceling each other out. And so in the end, I'm just going to go straight to this, to 2 minus x squared. All right, remember again, though, this question didn't actually ask for the derivative. It's asking for the slope when x equals -1, or the slope at that point. So I definitely want to clean this up, because this is really messy here. So a few things to do. Well, if I look at the numerator, really that whole first term is the same as just the square root of 2 minus x squared times by -1. Oh, sorry, the negative in the front is important. Plus x, if I look right here, this 1/2 and the 2 cancel out. There's also still a negative right here, so I'm actually going to just call this whole term negative. And what else do I have here? I have an x times another x, so I'm actually going to make this x squared. And all that is being multiplied by 2 minus x squared to the power of negative 1/2. So I'm going to write that as a fraction like this, as the square root of 2 minus x squared. And all this is over 2 minus x squared. All right, so at this point, remember again, the point of this was not to just to find the derivative, it was to find the slope at this point. And so my expression here, I think, is at a point where I feel pretty good about just substituting x with negative 1. Honestly, the y value for this point doesn't really matter to me. So I'm now going to let x equal negative 1. Let x equal negative 1. And so what do I get here? Ooh, looks a little bit messy. The good thing is negative 1 is a pretty nice number to deal with. Let me just double check I have everything correct here. All right, so at this point, just got to be careful with my calculations, but in the end, this should all simplify down to negative the square root of 1 minus 1 divided by 1 all over 1, which should all simplify to just negative 2. And so that is the slope of the tangent line that I showed you. The slope of that tangent line was negative 2, down 2 over 1. And so if I look back here, keep in mind the graph I gave you had no scales on the x and y axes, so it's definitely going down. All I can really tell from looking at the graphs is that the slope is negative, but I can't actually tell the slope is negative 2 because I don't actually have the grid lines, but now I know the slope is negative 2 at that point. And notice, since I wasn't actually asking for the derivative directly, I was asking for the slope at that point. I really just need to get the derivative to a point, simplified to a point in which, in this case, I could substitute x with negative 1 with relative ease. If I jump to that right here before I cancel stuff out, I think it has made it even more complex in myself. All right, but I think that's it. Yep, that's it from me.